Hi everyone, welcome once more to this YouTube channel at Best Science Brain YouTube channel. So today we're having a physics content, a simple harmonic motion. This time around, it doesn't involve a spiral spring, but rather we're going to oscillate using a meter rule. So the oscillation is called cantilever oscillation. Cantilever is a material which is fixed at one end and also fixed at one end while the other end is free to oscillate or move. So this is a physics experiment. Now, if you look at the diagram, all you need in this experiment is a meter rule, some masses, the G clamp, and sellotape, and also a horizontal surface like a desk. So you can see the desktop here. You see the meter rule is clamped at the 10 cm mark with the G clamp. The black arrow signifies the G clamp. That means the length of the meter rule that is projecting out from the edge of the desk is 90, which is 100 minus 10, which is a 90 cm. We have a mass. That mass is centered on the 45 cm mark, which is half of 90 cm. So that the arrangement or how the experiment is designed. Let's go to the questions and then we'll go to the experiment. The first step says climb the meter rule to the edge of the bench such that 90 cm of the rule projects from the edge as shown in the diagram above. In short, the rule is capable of performing oscillatory motion. So the meter rule should be clamped at the 10 cm mark. 2. Fix a mass m equal to 150 gram at the 45 cm mark of the meter rule. 3. Deflate the rule slightly such that it performs vertical oscillation. 4. Determine the time for 10 complete oscillations and evaluate the period, capital T. 5. Evaluate T squared or square of period. 6. Repeat the procedure for 4 other values of M, 200, 250, 300, and 350 gram. In each case, determine and record the corresponding values of small t with the time for oscillation, capital T, the period, and T squared. Tabulate the readings. 7. Plot a graph of T squared on the vertical axis against M on the horizontal axis, starting both axes from the origin 0 and 0. 8. Determine the slope S of the graph and intercept C on the vertical axis. 9. Evaluate K equal to 4 pi over S. 10. State the precautions taken to ensure accurate results. So these are the things we should do. We go back to the experiment, to the diagram. The desk could be a bench or a desktop where you fix your meter rule at the 10 cm mark, and then 90 cm we're projecting out. In some cantilever experiment, the mass that should be oscillated is normally placed or is mostly placed at the 100 cm mark. But we decided to design this experiment and place our mass on the 45 cm mark. So why not on the 100 cm mark? Because the masses we're using here are heavy. The highest mass we're using in this experiment is 350 grams. And 350 grams is too heavy to be placed on the 100 cm mark. So if you place 250 grams on the 100 cm mark and oscillate the meter rule, it's likely that the meter rule would break. So we have to choose a vantage position, which is the half of the projecting edge, half of 90, 45 to place our mass or masses. So that is why we do not look to take the edge. Had we were using solar masses like 50, 100, 150, 200, we would have chosen maybe 100 cm. And mind you, you do the experiment using a wooden meter rule that is flexible, not the one that is thick, so they can be able to oscillate. And you don't use a plastic meter rule. So let's go to the experiment. So on the whiteboard, we'll have our readings, the serial number, 150 grams. Okay, there's an error here, let's correct it. The serial number should be The masses should be here: 150 grams, 200 grams, 250 grams, 300 grams, and 350 grams. So that the masses we are about to oscillate, the serial numbers are 1, 2, 1, 2, 3, 4, and then 5. So let's start off the experiment. So for the experiment, we have a G clamp, we have a meter rule, which we're going to clamp at the 10 cm mark. So move it to around 10 cm and then clamp it here. So let's move it a little bit closer. Then very sure we'll clamp at the 10 cm. So here is 10 cm. So we can now move. So let's move this in. The G clamp is off from the desk, so it should be under the desk. So we are there. So the value here is 10 cm. The free end is 90 cm. So having done that, let's move our camera somehow backward for you to have a better view. So having done that, we'll now get a mass of 150 grams. So this mass is 100 grams. You can see 100, you can see 100 written on it. This mass is 50 grams. The two gives us 150. We're now going to select the mass at the 45 cm mark of the meter rule. So this is 45 cm. We're going to use the select to move it around firmly on the wood. Okay. Having done that, we'll make sure here is firm. Then we'll now set this mass into 10 vertical oscillations by slightly displacing the free end of the meter rule, keeping our stopwatch ready. We can count, and then when we are counting, we have to be fast about it because the amplitude dies rapidly with time, so the oscillation is not long-lived. So to oscillate, you lift it a little, as I did it, and then leave it to go. So the timekeeper is ready. Now we move. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 oscillations. So we now look for our time for 10 oscillations. Time for 10 oscillations, we have 9.58 seconds. 9.58 seconds. So recorded. We'll now repeat it. Repeat once more so that to minimize error. Repeat it once more to minimize error. Repeat it again. Leave the meter rule up a little and then leave it to dangle to oscillate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what's the time? 9.60 seconds. Record 9.60 seconds. As a second time, see there's a close range. We'll now find the average of the two. 9.58 plus 9.60 divided by 2. That gives us the average. When we do that, we get in 9.59 seconds. Then, having done that, we find the period. The period is divide this time 9.59 by 10 oscillations. That gives us 0.959, also in seconds. We now find the square of the period. You square the period, we're getting 0.920 approximately, 0.920 square of the period. So having done that, we move to the 200 gram mass. We remove the 150 gram mass, and then this is 100 and 100. Two of them put together making 200. Go to the 45 cm mark again, and then select this 900 gram, 200 gram rather, on the same 45 cm mark, and repeat the experiment as we did in the initial instance. So with this, let's see how we're going to do it. So now I have it, the 200 gram mass fixed firmly on the 45 cm mark. Then we now start oscillation. Timekeeper ready. So we lift it and then return your stopwatch to 0. Okay, let's start. We now move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a time of 10.9 seconds. 10.9 seconds for the 200 gram mass. Repeat it again. Repeat it so that we can have a second time. And then we'll move again. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10.7 seconds. 10.7 seconds. Average time becomes 10.9 plus 10.7 divided by 2. That gives us 10.8 seconds. Period, we divide 10.8 by 10. That gives us 0.108. So, square of the period, we will square 0.108, and that gives us about 1.17 seconds squared. 1.17 seconds squared. So, having done that, move to the third oscillation. Now we need 300 gram mass. So we need 300 gram mass is 100 grams times 3. So already we have 200 gram here. We now add this, making it 300 grams. So we now add this, that is 300 gram mass. We select it on the 45 cm mark as well, as we have been doing the others. That gives us 300 gram mass. Then having done that is 300 gram mass already there. Make it firm. And then we now, timekeeper ready with your time. We now move. Before we continue, let's look at what we have done so far so you can have a better view at the board. So you can see for the 150 gram mass, the first time recorded is T1, 9.58 seconds. Second time recorded T2, 9.60 seconds. Average time, which is T1 plus T2 over 2, which is 9.58 plus 9.c divided by 2. That gives us 9.59. Then period, capital T, is the average time, that is T over 10. 9.59 over 10 gives us 0.959. Then period squared is 0.59 squared, that gives us 0.920. Then going to 200 grams, the second one we did, our first time T1 on the board is 10.9 seconds. Then second time, we did the second time, then T2 becomes 10.7. Average time, which is T, is going to be 10.9 plus 10.7 over 2. That gives you 10.8. Our period is 10.8 over 10. Since it's 10 oscillation, that gives us 0.108. Then the period square gives us 1.17. So we'll go to the third one, which we want to do now. That is the 250 gram, the Okay, we did it should be 250, not 300. So we have to go and change the mass. 250, not 300. So we have to move on to the masses. We thought this 300 we have here. So since it's 250, we're going to add under 50. This 200 and then 50 giving us 250 gram mass. Then we now select it on the 45 cm, which is constant for this experiment. 45 cm mark. Then having done that, making sure it's firm, we can now oscillate the 250 cm. So our timekeeper ready. We now oscillate 250. Take the meter rule up. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what time do you have? 250, 11.40. So I have 11.40 seconds. Having done that, repeat it again so that we'll have a minimized error. So we'll go again, 250 gram, we'll move, oscillate, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Didn't even start. Let's repeat it again. Keep your stopwatch, return it to 0. So let's have it again. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we now have 11.8. We have 11.8 as from your time. So 11.80. So do the calculation, find the average. 11.40 plus 11.80 divided by 2. That gives us 11.60 as our average time. And then period divided by 10. We now have 1.16. Then square of the period. 1.16 square gives us 1.35. 1.35. So let's go through that work by raising our camera. For 250 gram mass, T1 gave us 11.40. T2 gave us 11.80. Average time, which is T1 plus T2 over 2, gave us 11.60. Then our period is 1.60 over 10. That is time over 10, giving us 1.16. Then the square of a period, 1.16 square gives us 1.35. We'll now go to the 300 gram mass, the fourth one, the 300 gram mass now. The 300 gram mass goes back to these masses. Remove the 50, remaining 200, we'll add extra 100. That makes it 300 on the same 45 cm mark. We select it firmly to the meter rule. Okay. Let's do it very well. To the meter rule. So having done that, we now oscillate the meter rule. That become move. So the timekeeper, please be ready. Take your time to 0. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what the time for 300 gram mass? Okay, 12.63 seconds. So we have 12.63 obtained in the first instance, as you can see it on the whiteboard, or after I can raise the camera for you. Then I repeat again, take the meter rule up and leave it to oscillate. So timekeeper, please return the time to 0. So 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're getting 13.01 seconds. 13.01 seconds. So the average time, you now add 12.63 to 13.01 and divide by 2. Do it. When you do it, you get 12.8 approximately. 12.8 0 or 2 decimal places, A0. Then the period, divide 12.8 by 10, you get 1.28. Then square the period, square 1.28, you get 1.64. So let's look at reading on the board. On the whiteboard, for the 300 gram mass, our T1 we got 12.63, our T2 got 13.01, our average time T1 plus T2 over 2 gives us 12.80. T1 plus T2 over 2, that's the average. 12.63 plus 13.01 over 2 gives us 12.80. Then the period, which is the T, 12.8 over 10, that gives us 1.28. Then T squared, which is 1.28 squared, that gives us 1.64. We'll now move to the 350 gram mass. So already we have 300 gram mass here. We'll remove, okay, we're not, this 300, we're adding additional 50 to make it 350 gram here. So we'll select this to the meter rule, make it firm. So you can use a select tape, you can use the black one, you can still use the masking tape or the white type. As long as it can give you a firm grip, that'll be okay. So we have our 350 gram mass here. So without any mistake, on the 45 cm mark. So you see that it's heavy. Look at the weight, the effect it's having on the meter rule. Now talk about when you bring it at the end. So that becomes going to be disastrous. So having done that, so we're going to oscillate the 350 gram mass. Our timekeeper, please return your stopwatch to 0, and then let's start. So we'll move it up. 1, 2, so get ready. 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The time is 13.29 seconds. So 13.29 here, obtained. Won't repeat it again, but this time around, so I can get a T2. So gently, so we'll leave it, lift it up and leave it. So get ready, return your time to 0. So ready? Okay, 1, 2, ready, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what time do you have? 13.35. 13.35 seconds. So to find the average time, you add 13.29 to 13.35 and divide by 2. And you divide that, that's going to give you average of 13.3, approximately 13.3. So to find our period, divide 13.3 by 10, that gives us 1.33. Then find the square of the period, 1.33 square, that gives us 1.77. So before we go to the plotting, let's take 1 minute to look at our board, the readings on the board. Once more, only 1 minute. So let's station our camera very well. So see that the mass is heavy, but thank God we are done with it. It slip off. So if you look at the readings on the board, when the mass loaded on the meter, we were 150 gram. The first time we got, it was 9.58 seconds. Second, 9.60 seconds. Average, which is T1 plus T2 over 2, that gives us 9.59. Then the period, which is the average time over 10, 9.59 over 10, that gives us 0.959. Then T squared gives us 0.959 squared, that gives us 0.20. When the mass was 200 grams hanging on the meter rule on the 45 cm mark, our time it was 10.9 seconds for the first experiment. Second one, 10.7 seconds. Average time got 10.80. Adding the 2 and divided by 2, 10.9 plus 10.7 over 2. Then the period is 0.108. Then the square of the period, 0.108 square gives us 1.17. Number 3, when the time was 250 seconds, so when the mass was 250 grams, the first time we obtained was 11.40. The second time was 11.80. The average time, 11.4 plus 11.8 over 2 gives 11.60. Then our period is 1.16. That divided 11.6 by 10, that's the period, 1.16. The square of the period, the 1.16 square gives us 1.35. Then when the time was 300, when the mass was 300 grams on the meter rule, then our time, first time was 12.63, then T2 13.01, average time 12.63 plus 13.01 over 2 gives us 12.80, then period is 12.80 over 10, that gives us 1.28, 1.28 square gives us 1.64. When the mass of the meter rule was 350 grams, our first time was 13.29 for 10 oscillations. Second time T to 13.35. Average time 13.29 plus 13.35 over 2 gives us 13.30. Then the period, which is small t over 10, is 13.3 over 10, gives us 1.33. Then period squared is 1.33 squared, that gives us 1.77. So move over to the plotting of the graph. So for the graphing, we have to write out what we need from the board. We are plotting t squared against m. This is not all the readings, but what we wrote out is what we need to plot. We are plotting t squared on the vertical axis against mass on the horizontal axis. So mass of 150 grams, the period squared is 0.920. Mass of 200 grams, the square of the period is 1.17 seconds squared. Mass of 250 grams, the period square is 1.35. Mass of 300 grams, the square of the period is 1.64. And mass of 350, the square of the period is 1.77. So on the vertical axis, we have t squared or seconds squared. We have the values there written down. The least value is 0. We have to start from 0, followed by 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8. So what it means that on the vertical axis or on the t square axis, we have 0.2 unit to 2 centimeter. So going to the horizontal axis, we have, which is the mass axis, mass in grams. We have 0, 50, 100, 150, increasing by 50 interval. So on the horizontal axis, we can say we have 50, there is 2 cm to 50 unit. So we'll now plot our graph. So for us to understand the graph, that means for the horizontal axis, one tiny line is 5. Since there are 10 tiny lines in one bus, so one tiny line is 5 unit, 5, 10, until now reach 20. And for the vertical axis, one tiny line is 0.02, 0.02. So you count 10 lines to give you 0.2. So let's take our value. 150 grams goes with 0.92. So let's get 0.9. We're plotting to two decimal places. So 150 grams go with 0.92. So this is 0.8. The next line is 0.82. Second line is 0.84, 86, 88, 0.9, 0.92. So that should be there. The workplace I spotted 0.92. We'll go with 150. So that is it. 0.92 goes with 150 on that spot. The next is 200 grams go with 0.17. 200 with 1.17. So look at 1.17 from the graph on the vertical axis. So this is one whole number, and as I said, one tiny line is 0.02. So the next is 1.02, 1.04, 1.06, 1.08, and then 1.1, 1.12, 14, 16, 18. So it should be between 1.16 and 1.18. That is where you have 1.17. So at that point, it will go to 200. So you can see 1.17 goes with 200 on the horizontal axis. The next is 300 going with 1.64. 300 going with 1.64. So this is 1.6. The next line is 1.62. This one line is 1.64, which should be here. So that will go with 300. So you can see 1.64, that is there, goes with 300 on the horizontal axis. We omitted 250, so we have to plot 250. We didn't plot that of 250. So we skip 250. So we have to insert 250. So 250 grams go with 1.35. So 250 have to be done before 300, but there's no problem. We can still do 250. So 1.35 goes with 250. So let's count off 1.35. This is 1.2, 1.22. The next one, 1.24, 1.26, 1.28, 1.3, 1.34, 1.36. 1.34 should be between 1.34 and 1.36 at the middle. So that's the point. So you can see 1.34, 35 going with at the spot there, going with a 250. I think let's get it right. Yeah, that should be there, going with 250 down there. So remaining one more point, 350 grams go with 1.77. 350 goes with 1.77. So let's go and locate 1.77 from the graph. So this is 1.662, 1.6, 62, 64, 66, 68, 1.7, 72, 74, 76, 78. So 1.77 is between 1.76 and 1.78 at the middle there. So that will go with 350. So let's check the coordinates again. 1.77 going down. You can see the point up there. And then coincides with 350. So let's join the points. We look at the points. It appears that we'll have a good experiment of almost all the points on a straight line, except more like 1 point is off from the straight line. 4 points are on it, 1 point is off. So you have a baseline drawn there with 3 points perfectly in the line and 2 points close to the straight line. So that's a good experiment. We'll take our slope. We're going to take our slope between the first point, the highest point there for the 350 grams, and the least point. We'll take our slope with this interval. So the diagram is drawn from the highest point to the least point. That's why we're taking our slope, because those points fall into the straight line. So you can see that. So let's go to the working. So say slope equal to change on t squared axis all over change on mass axis, which should be the coordinates on the t squared. The highest point is 1.77 minus the lower point 0.92, or in seconds squared all over. The coordinates from the horizontal axis is 350 minus 150. That's the mass in gram. So 1.77 minus 0.92 will give us 0.85 seconds squared. 350 minus 150 gives us 200 grams. Convert to kg, divided by 1,000, that gives us 0.20 kg. So we'll divide 0.85 by 0.20. We're going to get in 4.25 seconds squared per kilogram. Then the next question, we're asked to find the intercept on the vertical axis, C. So we have the intercept on the vertical axis. That intercept is roughly 0.3. between 0.2 and 0.4. So intercept C is 0.30 seconds squared. The next we have to calculate K. K equal to 4 pi over slope. And pi is 22 over 7. So we evaluate 4 times 22 all over our slope is 4.25 all over 4.25, then times 7. That's all over 22 over 7, of course. So you now do 4 times 22 all over 4.25 times 7. That gives us 2.96 kilogram per second squared. Inverted the unit of the slope, you get the unit of the evaluation K, constant K, kilogram per second squared. The next is precaution for the experiment. So what are the precautions for this experiment? The first precaution, one would say, can say, I ensure the meter rule was firmly clamped. The meter rule was firmly clamped to the desk. That's one of the precautions. Number 2 precautions, I ensure that I repeated each experiment. I ensure that I repeated each experiment. You can see we did it to each of them, we did it twice, T1, T2, and to the average T to minimize error. Then the third precaution could be, I ensure that I avoided error due to parallels when reading the stopwatch. So I avoided error due to parallels when reading the stopwatch, or zero error was avoided when reading the stopwatch. So these are the precautions that are necessary for this experiment, so which involve cantilever oscillation. So thank you for your time. If you are not subscribed to the channel, tap on the subscription button at the video is playing. The subscription icon is beneath the video. Tap on it and get subscribed. Share the video to somebody that needs it.